Something changed on the morning of December 16th, a shift so quiet it slipped beneath the noise of a dozen observatories, but the math didn't lie. When 3i Atlas crossed a threshold just 1.8 astronomical units from Earth, the data changed. Acceleration patterns diverged, light curves flattened, and planetary defense centers, both in the US and across Europe, entered silent protocol. They didn't send out a press release, they never do. But new targeting vectors, updated every 4 hours, showed the unmistakable signs. Something near Earth had just triggered a multi-agency response, and it wasn't an asteroid. It was the third confirmed interstellar object ever detected. 3i Atlas. It has never obeyed the laws of comet physics. It never broke apart at perihelion, and its anti-tail, an emission that points toward the Sun, is still active. Now, that object is drifting closer than predicted, and the trajectory doesn't match solar radiation pressure or outgassing. It matches intent. Over the next 22 chapters, we're going to dissect exactly what happened on December 16th. We'll examine the new tracking data, the shifts in tail structure, the sudden narrowing of infrared emission, and the magnetic echo detected by the Parker probe just moments after the object passed Earth's magnetic boundary. But most importantly, we'll ask why planetary defense simulations were rerun 5 times between 02 GAD and ISO 8 LAS UTC that morning. Because if 3i Atlas isn't a comet, and the patterns continue, it means we're not just tracking an object, we're being observed. On the surface, nothing had changed. NASA's Near-Earth Object Center continued its hourly cadence. The Jet Propulsion Lab in Pasadena still published open datasets. But buried inside the raw orbital logs was a small anomaly, barely a blip. The December 15th trajectory placed 3i Atlas well within safe bounds, outbound, predictable, fading. But by the early hours of December 16th, a secondary vector was added. Internally marked T-Path 4, it suggested a conditional adjustment, a hypothetical alignment. Except this wasn't a hypothetical model, it was an active computation. Analysts watching the public data stream noticed a narrowing band in the orbital error margin. These are statistical cones used to predict future positions of celestial bodies. And when planetary defense systems are triggered, those cones become thin, deliberate lines. Some call it threading the keyhole, others a soft lock. But behind closed systems, something more urgent was happening. The European Space Agency's NEO Coordination Centre activated its passive surveillance threshold. That's a quiet escalation. No alarms, no briefings, just recalibrated antennas and new angle prioritizations for the upcoming Earth-passing window. And this wasn't routine, because 3i Atlas wasn't behaving like a fading object anymore. Its light curve, previously erratic, had stabilized into a plateau, and its outbound, acceleration which had once aligned with solar radiation pressure, now appeared neutral, dead straight and flat. Almost like it had stopped adjusting. The silence was telling. No press releases, no emergency sessions. But those who know where to look, who watch the quiet corners of space traffic control, saw the pattern. Something had crossed a threshold, and whatever it was, it triggered a response designed not to cause panic, but to prepare, and that was just the beginning. The outbound path of 3i Atlas was supposed to be clean. After its perihelion slingshot near the Sun on October 30th, orbital models projected a slow and stable arc, drifting outward, away from the inner planets, fading gently into the outer solar system. But as of December 16th, that projection no longer held. Ground-based observatories from Chile, Hawaii, and the Canary Islands reported an unexpected flattening of the outbound arc. In the language of celestial mechanics, this wasn't a gravitational deviation, it was a momentum collapse. The object had not slowed visibly, but its departure angle had narrowed, shifting closer to Earth's orbital plane. Normally, such shifts are explained by outgassing, a natural force produced when a comet vents sublimated ice and dust from its surface. But 3i Atlas showed no new jets. The infrared signature remained unchanged. The coma, once active and layered with carbon dioxide vapor, had gone eerily still. It wasn't pushing away from Earth anymore. Instead, it was matching a curvature that followed Earth's motion, like a boat adjusting its sail to follow a coastline rather than drift out to sea. Tracking algorithms had to be rewritten. The typical outflow model, where solar heating leads to tail formation, which in turn causes rotational torque, no longer applied. There was no observed torque, no coma thickening, no spin. And that's where things began to spiral. JPL's trajectory database updated at 03:12 UTC. Normally updates lag behind real-time observations by a few hours due to processing. But this one came fast. Too fast. It was accompanied by a new non-gravitational perturbation coefficient, flagged with the same internal code previously used for Oumuamua in 2017. The signal was simple but profound. 3i Atlas wasn't behaving passively. An object drifting through the solar system should never correct its path after perihelion. Solar pressure should push it out in a clean, widening ellipse. But now the outbound arc had narrowed toward a corridor, one that intersected Earth's orbital path within a 92-hour window. Still, the public-facing models showed no threat. The distance? Over 160 million miles. Too far for concern. But the shape of the path wasn't the point anymore. It was the intention it implied. Because the only objects that adjust trajectory in this way are guided ones. And if it wasn't gravity, and it wasn't outgassing, then whatever caused the curve in its outbound route was coming from the object itself. A force with no source, a movement with no thrust, and a planetary defense network that stopped calling it a comet. For weeks, astronomers had watched the tail of 3i Atlas behave like no comet they had ever tracked. Ionized particles danced outward in sharp symmetrical streams, some forming arcs, others firing directly sunward in defiance of physics. But on the morning of December 16th, something happened that sent a ripple through the space weather community. The tail stopped moving, not faded, not thinned. It paused. At 04:18 UTC, the Solar and Heliospheric Observatory, SOHO, recorded a 6-minute window during which no tail movement was observed in the ultraviolet band. Normally, cometary tails shimmer with continuous activity. Dust particles and ions respond to solar wind fluctuations and photon pressure, creating a turbulent, flickering structure. But in that moment, just before Earth entered the outer boundary of 3i Atlas's projected radiant corridor, the tail aligned into a rigid, blade-like line. No shimmer, no undulation, just absolute stillness. That observation triggered a chain of cross-checks. The Parker Solar Probe, which had been monitoring magnetic flux in the same quadrant, reported no sudden drop in solar wind velocity. In fact, space weather remained constant. There was no coronal mass ejection, no shock front, no solar anomaly to blame. This wasn't the environment pausing, it was the object. Infrared tracking from the Subaru telescope in Hawaii supported the claim. The thermal glow that typically surrounds active comets had tightened, drawn inward, as if the outgassing had been paused or interrupted by something internal. The coma did not disperse, it contracted, almost like an engine winding down. By 04:24 UTC, the tail resumed its normal motion, but it didn't pick up where it left off. It restarted with a new alignment, angled 7 degrees off its previous axis. That wouldn't mean much, except for one thing. The new axis pointed directly between Earth and the Moon. Orbital analysts call this a corridor pivot, a micro-adjustment made by satellites or probes to align with a moving planetary target. Except this wasn't a satellite, and no known natural body executes maneuvers this clean. What followed was even more troubling. For 12 minutes after the tail resumed motion, the reflected light pattern on the object's surface exhibited what astronomers call phased symmetry. In simpler terms, it looked like the tail and the object's reflective surfaces were now linked, coordinated, responding to something internal rather than external. That raised a question no one wanted to say out loud. Was this system adjusting its thrust? Comets don't have thrust. They don't manage tail geometry like spacecraft, and they don't pause emission to recalibrate alignment. But the data didn't lie. Multiple observatories confirmed it. The tail paused, the coma contracted, the axis realigned, and the glow shifted with it. Some tried to explain it away, maybe a transient magnetic disturbance, a sudden solar shadow, a photonic artifact. But each explanation collapsed under one detail: the timing. Because this alignment shift occurred just as planetary defense systems worldwide began requesting new observation angles. As if the object noticed, as if it responded, and that response wasn't fading into space, it was focusing. By Esquifaviosi UTC on December 16th, a new thermal scan came in from the French Guiana Earth Observation Complex. Designed to map high atmosphere temperature changes, it rarely tracked deep space objects. But for the first time in its operational history, the facility redirected its long-range thermal sensor array to focus on 3I Atlas. What it found stunned the control team. The thermal signature from the object's nucleus had changed in pattern, not in intensity, but in symmetry. Instead of a broad, diffuse core typical of cometary outgassing, 3I Atlas now emitted a concentrated, bilaterally balanced heat plume. Two hotspots, equidistant from the nucleus center, glowing with equal intensity on opposite flanks. That's not comet behavior. Natural outgassing from a rotating nucleus is chaotic, staggered, and usually favors one hemisphere. But this wasn't random. It looked mirrored, and in aerospace thermography, mirror symmetry is a hallmark of controlled surface discharge, what we'd expect from engineered venting. Somewhere inside European Space Agency databases, engineers began comparing the thermal pattern to known propulsion systems, ion vents, radiative cooling fields, thermoelectric plates. The match wasn't perfect, but it was closer to artificial systems than natural ones. Meanwhile, the James Webb Space Telescope, operating in its mid-infrared mode, picked up on the same symmetry. Its powerful sensors spotted a narrow, cold seam running lengthwise across the object, cooler than its surroundings by nearly 25 Kelvin. That seam divided the nucleus into two lobes, each glowing with nearly identical thermal output like wings. But comets don't have wings, and they don't divide their heat signatures along geometric lines. By ZO 522 UTC, the thermal lock became even clearer. The hotspots were not just stable, they were rotating, slowly, but precisely. Not wobbling like a tumbling comet nucleus, tracking like gyroscopic stabilizers, and the rotation speed, exactly one full axis roll every 6 hours, the same frequency detected 3 weeks earlier during the Antitail's first appearance. This wasn't a coincidence, this was coordination, a thermal feedback loop responding to positional inputs. But where was it taking direction from? The answer came from an unlikely place, deep space radar. A narrow-band radar ping from the Goldstone complex in California, sent earlier as part of routine tracking, bounced off the object's surface and returned a signature that revealed something no comet should show: phase coherence. This means the radar bounce came back in a clean, structured wave, not scattered by a porous, irregular surface, but returned like it had struck something smooth. Not metallic necessarily, but dense, flat, angular. Thermal imaging confirmed it, radar confirmed it, and the slow gyroscopic roll showed intent. 3I Atlas was no longer hiding in chaos, it was now showing symmetry, and symmetry in nature is rare. In spacecraft, it's a requirement. At 5:45 UTC, a small but significant anomaly was flagged by the Wide-Field Infrared Survey Explorer, WISE, operating in passive observation mode from low Earth orbit. It wasn't part of any scheduled tracking of 3I Atlas. The signal came by accident, and that accident changed everything. WISE detected a brief but unusually strong albedo spike, an increase in reflectivity, coming from 3I Atlas. At first, it appeared to be a glitch. Reflectivity curves for interstellar comets follow predictable paths, rising gradually near perihelion, then declining as ice and dust scatter incoming sunlight. But this spike didn't follow that pattern. It was sharp, sudden, and, most importantly, targeted. At exactly STO 5:44 Tworsost UTC, the object's surface emitted a pulse of reflected light that matched the angle of Earth's rotational tilt, 23.5 degrees off vertical. The beam wasn't visible to the naked eye, but in infrared and polarized light, the spike looked almost surgical, like a mirror pivoting into alignment. This led to an urgent cross-confirmation request from the National Solar Observatory. Within 3 minutes, 3 separate optical telescopes confirmed the same result. One in La Palma, one in New Mexico, one on the Indian coast. All recorded the same reflected spike within a 1-second window, something previously unseen in cometary observation. It wasn't just brightness, it was directional reflection. And directional reflection doesn't occur unless an object's surface is adjusting to a known source, like light bouncing off a mirror that knows where the flashlight is coming from. Analysts went to work, polarimetry data, used to measure how light bounces off dust particles, suddenly showed a linear alignment across the coma, something that only occurs when the reflective surface is smooth, planar, and stable. The scatter pattern changed shape entirely, transforming from a radial dispersion into a flat corridor. That corridor. It faced Earth's night-side hemisphere, a literal lock-on. Of course, skeptics immediately pointed to coincidence. Perhaps Earth's orbit had lined up in just the right way to create a fluke of reflectivity. Perhaps the coma's composition changed abruptly. Perhaps the object rolled naturally into position due to internal instability. But every theory collapsed under one detail: the timing. Because Earth was not yet directly between the Sun and the object. And yet the mirror-like signal aligned, not with the Sun, but with Earth. That distinction matters. If sunlight had been the source of the reflection, the beam would have pointed outward, but this spike bent backward, toward the only other object in space emitting a weak but measurable frequency of directed signals: us. The signal was quiet. It lasted less than 8 seconds. But 8 seconds was enough to trigger a reflective feedback loop in the object's outer layer, captured again 20 minutes later by ESA's solar orbiter as it passed behind the object's path. It saw the tail shift again, this time not from solar wind but from internal redirection, as if the whole body had subtly rolled to maintain the reflective vector, like a satellite adjusting solar panels. There was no announcement, no public warning. But internal documents from a European telemetry centre leaked one phrase later that morning: reflective alignment achieved. Stability suggests active tracking configuration. What they meant: it was no longer just reflecting sunlight, it was reflecting us. Most comets are surrounded by dust clouds, fragments, vapour, and gas sublimated from the nucleus. These clouds shimmer, they stretch and contract. They scatter light unpredictably depending on solar wind pressure and the composition of the debris. But 3i Atlas had a different kind of cloud. By 6:20 UTC on December 16th, the Atacama Large Millimeter Array in Chile observed something that should not exist in the upper layers of a comet's coma: a static shell. Using millimeter wave imaging, the array picked up a distinct outer boundary, a shell of particles that maintained its shape despite solar interference. It was not expanding, it was not venting outward, it was simply holding. That finding defied expectations. When solar radiation hits cometary dust, the smaller particles disperse first. It's a chaotic process, and the result is always an expanding cloud. But this shell stayed the same thickness for over 11 minutes of continuous observation. Even more confusing, the particles in the shell weren't scattering sunlight. They were absorbing it, then re-emitting it with a delay of nearly 2.7 seconds. In the world of spectroscopy, that's not just abnormal, it's unprecedented. It implies a controlled re-radiation process, something that traps energy and lets it out in discrete waves. This wasn't a dust cloud, it was a containment layer. Theories spread quickly through internal channels. Could it be an electromagnetic field? A resonant ring of charged particles? A shell formed by electrostatic cohesion rather than by sublimation? But none of those answered the most important observation: the shape. Unlike normal comets, which form spherical comas, this one was elliptical, a stretched oval with 2 poles, and those poles, coincidentally, matched the reflective axis observed earlier in Chapter 5. Which meant one thing: this cloud wasn't passive, it was structured. The outer edge of the shell flickered with intermittent hotspots like beacons, not continuous but timed. Polar pulses emanating at 6-minute intervals, detected across the L-band and faintly in S-band. These pulses weren't natural, and yet they came from dust, if it was dust at all. The shell held for 43 minutes before fading, but when it faded it didn't disperse, it collapsed inward, as if the structure folded rather than dissolved. The core remained intact. The tail adjusted. The reflectivity dropped. But not one particle of the shell showed free-floating motion. Nothing scattered. And for the teams watching from 5 continents, only one conclusion remained viable. This was no random coma of particles drifting in space. This was a shield, a static, timed, responsive envelope, folding and adjusting to positional cues, one that defied every known comet model and one that had just aligned its final edge toward Earth. At 0644 UTC, a subtle distortion was recorded by the Parker Solar Probe as it passed through a relatively calm patch of the solar wind near Earth's orbital track. On most days, such fluctuations wouldn't raise alarms, but on December 16th, every data feed tied to the path of 3I Atlas was under active scrutiny. So when the distortion didn't match any local solar activity, attention shifted fast. What the Parker probe detected was not a magnetic storm. It wasn't even strong enough to qualify as turbulence. It was something quieter, stranger, a magnetic echo. Magnetic echoes are rare in heliophysics. They occur when a structure interacts with the solar wind in such a way that it leaves a backscatter signature, an electromagnetic bounce that returns through the charged medium. It's not unlike sonar in water, but in space, where magnetic fields stretch across millions of kilometers, echoes like this should disperse. This one didn't. The echo originated from a localized point, matched within a 20-minute telemetry window to the path of 3I Atlas. More than that, it traced to the moment when the object's reflective spike had pointed directly at Earth. A clean triangle emerged: object to Earth, Earth to echo, echo to probe. That's not turbulence, that's geometry. The frequency, just under 2 MHz, faint, non-modulated, but persistent. And here's what made it even more unusual. The echo contained harmonics. Not random, but spaced. A series of intervals that could not be attributed to known solar oscillations. When space physicists reviewed the data, they found that the echo followed a ratio consistent with resonant frequency, bouncing from layered conductive materials. In plain terms, the echo sounded like it had structure. And structure meant boundaries, plates, panels, edges. Natural bodies don't reflect magnetic fields with defined harmonics. They absorb, they scatter. But this signal bounced, clean, as if it had met something that held its form under solar pressure. And that's when the calls started. Heliophysics teams from ESA, NASA, and the Chinese National Space Agency initiated a rare 3-party data sync. It wasn't a public exercise. These institutions don't usually collaborate in real time, but the shape of the magnetic curve couldn't be explained away. The echo behaved like a signature, something bouncing back, and its shape was brief but unmistakable, an inverted V structure with symmetrical return slope. This resembled something known in aerospace, the radar profile of wedge-shaped stealth platforms. Not a perfect match, but uncomfortably close. The idea that a comet could reflect space magnetism like a stealth craft should be absurd. And yet, the harmonics didn't lie. The timing also aligned with the narrowing of the outbound arc seen in Chapter 2. As the object had shifted trajectory, it left behind this magnetic fingerprint, not by accident, but as if it knew how. Parker Probe's instruments continued tracking for 30 minutes. The echo faded, no repetition, no signal trail. But before it vanished entirely, one final harmonic rang out, just above background noise, in the same band used by early SETI sweeps. The scientists wrote it off as coincidence, but they filed the pattern anyway, and they assigned it a tag not normally used for comets: reflective field event, confirmed. Something in space had bounced energy, not light, not heat, but magnetism, and that changed the rules of what a comet could be. As Earth's rotation brought Asia into daylight, new imaging feeds from Japanese and South Korean observatories went live. One of them, located atop Mount Norikura, had recently been upgraded with an experimental high frame rate optical filter. At 0712 UTC, that filter captured something strange. While tracking 3I Atlas across a narrow sector of sky, the telescope recorded small, rhythmic dimming events across the object's surface, dips in brightness that cycled every 24 seconds. At first, it seemed like instrument error, atmospheric distortion, but the skies were clear and the filter log showed no anomalies. These weren't random, they were patterns, like flickers. The team reprocessed the footage using contrast amplification. What emerged was something no one expected: a sequence of rotating surface zones, dark, reflective, then dark again, passing across the object like rotating panels or windows catching and losing light at precise intervals. But comets don't have panels. They don't rotate with surface patches that create consistent reflectivity dips. And yet, This one did. The object was spinning, slowly, but with regularity. Every 24 seconds, a specific region on the object's surface passed the Earth-facing side and reflected light differently from the surrounding structure. The signature repeated 3 times before fading, then reappeared in sync 30 minutes later. This wasn't sublimation, it wasn't dust plume variation, this was surface behavior, using interpolation modeling. The observatory estimated a surface geometry consistent with a faceted shell, possibly hexagonal or triangular in repetition. A tessellated structure, not smooth like an asteroid, not granular like a comet, but angular, intentional. That kind of geometric lock is only known in one field: thermal shielding, or precision signal modulation. The implications are not lost on anyone familiar with spacecraft engineering. Later that morning, the Korea Astronomy and Space Science Institute tried to duplicate the observation using infrared. They found faint heat ridges matching the same rotation cycle. Not hot, but structured. It was as if the object's surface was divided into regions, some absorbing solar energy, others deflecting it. Some appearing dark, some highly reflective. Each cycle was synchronized, each reflection timed, to Earth. One analyst summarized it bluntly: "This is the first time we've seen rotational modulation on a comet that behaves like an optical array." That phrase, optical array, raised flags. Because optical arrays aren't natural, they are built. And now, all eyes were on the object's approach, because if those rotating panels were scanning, then 3i Atlas wasn't drifting, it was watching. By 7:39 UTC, the situation moved from strange to structured. NASA's Deep Space Network had been actively monitoring 3i Atlas with its array of radio dishes in Goldstone, Canberra, and Madrid. These antennas aren't designed just for communication. They're also used for radio eco-ranging, the process of pinging distant objects with low-frequency pulses and listening for reflections. What they received was unexpected. When the Goldstone transmitter sent a burst toward 3i Atlas at precisely 07:36 UTC, the signal should have taken just under 20 minutes to bounce back. What returned wasn't just one echo, it was 2. The first was faint, consistent with what one might expect from a loosely packed icy body, but the second, sharper, delayed by less than a millisecond, and carrying a different spectral signature. It had structure. To understand why that matters, we need to explain the concept of echo layering. When radio signals bounce off a natural object, like an asteroid or a comet, they return scattered and weak. If the object has voids or is porous, some of the signal is absorbed, some distorted. Rarely does it return in a tight pattern, but if the surface is solid, if it's smooth or faceted, the signal can reflect off multiple planes before returning. That's what happened here. The second echo showed harmonic consistency and angular return time spacing. It resembled what engineers call a multi-bounce resonance wall, the kind you find in radar reflective chambers or off the surface of metallic panels. In practical terms, it was as if the signal had hit a wall, reflected off an interior surface and bounced back, and it didn't stop there. Within minutes, similar echo structures were confirmed from the Madrid and Canberra antennas. They all bounced the same way, same timing, same spread. And the object's position hadn't changed, but something else had. The strength of the second echo wasn't declining with distance, it was amplifying, as if the object was tuning its surface in response. This process is known as active reflection in satellite communication, the ability to shape or amplify a returning signal to increase coherence. But comets don't amplify radar, they don't redirect electromagnetic feedback, they don't have walls. Yet 3i Atlas now showed a clear, timed directional bounce pattern, one that repeated in intervals of 4. 4 panels, 4 returns, 4 faces, nobody could say for sure. What was clear? The echo structure only appeared when the object's rotational phase lined up with its Earth-facing side. When the panels passed behind, the secondary echo vanished. Then it returned on the next cycle, same delay, same strength. The implication was chilling. This wasn't an object passively moving through the solar system. It was reflecting, echoing, modulating, not to signal, but to read, to gauge, to watch what was watching it. Later that day, the anomaly was given a formal designation in the tracking logs. EE3I, Echo Event Level 3 Intelligence Suggested. That label is rarely used. Only once before, and that time, It was quickly retracted, but this time the data was public and the wall had spoken back. At 8:04 UTC, a new observation came in from the Very Large Telescope, VLT array in Chile. The target was simple: capture high-resolution optical imagery of 3I Atlas as it passed through a clean atmospheric window. The goal? Compare coma geometry to previous images from 1 week earlier. What the VLT captured changed the entire framing of the object. The coma wasn't expanding, it was conforming. Using a sequence of stacked long exposure frames, researchers created a composite image of the object's outer halo. The pattern wasn't random, it was angular, a polygon, specifically a hexagon. Hexagonal geometry in comets is unheard of. Sublimation and dust do not form symmetric shapes. The chaotic ejection of volatile gases doesn't resolve into clean angles. But here, 6 vertices, 6 vectors of dust flow, each spaced evenly. To confirm, the team isolated the spectral light emission from each vector. All 6 channels emitted carbon dioxide, but each one also carried trace differences, slight phase shifts in the emitted infrared radiation. This suggests they weren't ejected at the same time, but in sequence, as if they were firing in a cycle. That observation is important, because sequencing implies control, and the shape, a hexagonal field, points to something else in aerospace engineering: phased array fields. In terrestrial technology, phased arrays are systems used in radar and communication. By shifting the phase of multiple signals, they can steer beams or scan areas, without physically moving the array. Now consider this. If the hexagonal vectors around 3I Atlas were phased, if they were emitting particles in a controlled pattern, then this object wasn't just reacting to sunlight, it was steering, or scanning, or both. A secondary finding deepened the mystery. By overlaying the vector angles with Earth's orbital position, analysts discovered a startling alignment. One of the hexagonal arms pointed directly at Earth's trailing orbital path. Not where Earth was, not where it would be, where it had just passed. That meant the emission wasn't targeting Earth itself, but Earth's wake, the space it had moved through just hours earlier. Why? There's only one known use case for wake scanning in deep space: telemetry harvesting. In other words, reading what a planet leaves behind. No comet does this. No natural object should even know to try. But now a pattern emerged. 6-point ejection. Phase delay between arms. Light alignment with planetary wake. It wasn't random. It was designed to reflect, to bounce, to track, to mirror. At 8:36 UTC, the conclusion was no longer avoidable. 3I Atlas was scanning Earth's wake. It began with an anomaly recorded by the Arecibo Surrogate Radar Array in Western Australia, which had been observing the sky sector just behind Earth's orbital path. Their instruments had been retuned for a new planetary magnetic field drift experiment. But what they intercepted wasn't local magnetism, it was interaction. The signal came as a fluctuation in the ultra-low frequency band, something between electromagnetic noise and structured reflection. But as technicians examined the waveform, they found a consistent oscillation repeating every 4.9 seconds, stretching across 2 full minutes. And it was moving. The wavefront wasn't coming from Earth. It was emanating from the space behind Earth's path, specifically the L2 point zone that Earth had passed through just 15 hours earlier, and at the edge of that sector was 3I Atlas. What made this even more unusual was the signal's movement. The waveform didn't propagate randomly, it tracked along Earth's orbital trail. It was as if something was feeling through space, mapping variations along a path we had already travelled. In astrophysics this is unheard of, but in aerospace engineering it has a name. It's called wake scanning. Spacecraft use it to gather delayed telemetry, measuring what a target leaves behind rather than what it emits directly. It's a passive technique, covert, low energy, and difficult to detect. And now, an object we still called a comet was executing it with surgical precision. Further evidence came from the ESA's Gaia Observatory, which captured a near-infrared trail trailing behind 3I Atlas, not from its tail but from its forward arc. A stream of weak thermal excitation was being pulsed into the orbital plane, like sonar. It wasn't strong enough to alter the environment, but it was consistent and deliberate. The pulses matched the oscillation from the radar anomaly. Then came the most compelling proof. Actual 851 UTC, the United Kingdom Infrared Telescope, UKIRT, captured a set of microflashes in the same wake zone. The flashes were evenly spaced, faint, but unambiguously real. This was not a reflection from Earth. Earth had already moved on. These were delayed responses. It was like 3i Atlas was pinging the space Earth had moved through and watching for changes in residual energy, heat, or charge. No comet has ever demonstrated this kind of behaviour, and the spacing precisely matched the Earth-Moon distance, mapped backward through time. That detail sent a shock through the Planetary Defence Coordination Group, because if an object isn't targeting Earth directly, but targeting the wake instead, it may not be studying us biologically or visually. It may be analysing trajectory stability, our movement, our rhythm, our footprint in space. That's not surveillance, that's pre-calibration, as in calibrating something before direct engagement, and suddenly all the data converged: the echo wall, the rotational lock, the reflective modulation, the hexagonal phased emission, and now, wake scanning. It all formed a chain, a sequence, a checklist. It wasn't drifting. It wasn't responding randomly to solar pressure or gravitational flux. It was methodical, reading, adjusting, tracking. Every action matched a known technique from satellite-based targeting, signal harvesting, or reconnaissance scanning. It was as if 3i Atlas was running a diagnostic, not of our planet but of our presence, of how we move, how we heat space, how our systems interact with interplanetary dust, light, and time. And in doing so, it passed a threshold. This wasn't a comet anymore. This was a scanner, and it was nearly done scanning. At 09.10 UTC, the antitail returned. But this time, it did something no cometary structure had ever been recorded doing. It reversed. Normally, a comet's antitail is a rare optical phenomenon. It's caused by the unique geometry of Earth's position relative to the object and the Sun, making earlier dust emissions appear to stream toward the solar centre. It's an illusion. Perspective trickery. The dust isn't truly moving backward. It just looks that way from Earth's vantage point. But 3i Atlas wasn't following those rules. At exactly 09 UTC, the Large Binocular Telescope in Arizona captured a widening arc emerging from the object's sunward side. This arc wasn't shaped like a normal jet or plume. It was thick, structured, and more importantly, it was moving, not away from the Sun, but turning back toward it. Within 3 minutes, the antitail curved inward, not because Earth's angle changed, but because the object rotated, slowly, precisely. With a half-degree pitch, the structure that had been emitting dust backward now pivoted forward and aimed directly at the solar vector. From Earth, it appeared as though the antitail had reversed direction, but the science said otherwise. The structure was pivoting to face the Sun, deliberately. In solar physics, there's no reason for a comet to do this. The Sun-facing hemisphere should be venting the most gas and dust due to direct heating, but such plumes always trail behind, pushed by solar radiation. This one fought it. The antitail didn't curve passively. It held shape, even against solar wind resistance, and the curvature of that structure was extraordinary. Using volumetric modelling from the LBT data, researchers found that the arc maintained a 14-degree span for over 11 minutes, during which the solar wind speed measured 421 kilometers per second. That kind of stability doesn't happen in nature. Dust should scatter, gas should disperse. But this arc held its shape and orientation, even as it rotated forward. This wasn't an antitail anymore, it was a boom. In aerospace design, a boom refers to a long, narrow extension, often used to stabilize satellites, deploy antennas, or emit particles in controlled directions. This structure looked like a radiative boom, and what's more, it was glowing. Infrared readings showed a narrow thermal rise just along the arc's edge, like a heating element. And in ultraviolet, the entire boom pulsed 3 times over the course of 90 seconds. Each pulse coincided with solar magnetic field fluctuations. That timing suggested not just movement, but interaction, as if the boom wasn't pushing against the Sun, but communing with it. Somewhere in the ESA's telemetry logs, a note was added to the object's dynamic profile. Boom alignment likely. Anti-tail now displays properties consistent with stabilized solar interface platform. That phrase meant one thing. It was no longer venting dust, it was conducting. And if it was conducting, it was building charge, measuring fields, or emitting data. Whatever its function, 3i Atlas had flipped its most controversial feature from illusion to interface. The anti-tail wasn't reversing, it had finally locked. At 0921 UTC, a pattern emerged within the pivoted anti-tail of 3i Atlas. It wasn't the dust itself, it was the space around it. The James Webb Space Telescope, which had reoriented its mid-infrared instruments to track 3i Atlas's strange solar-facing arc, detected something unexpected: geometrical consistency in the dust stream's perimeter. Specifically, the emissions didn't simply spread in a cone, they shaped themselves into a polygonal dispersion zone, hexagonal, precisely six-sided, with internal radial symmetry. At first, this was thought to be a diffraction artifact, a kind of lens mirage caused by JWST's segmented mirrors. But when the team repeated the same readings using ground-based interferometry in Chile, the shape persisted. This wasn't an imaging illusion, it was real geometry forming in open space. Even stranger, the hexagonal pattern was rotating, not chaotically, but synchronously with the core's own observed motion. This rotation locked every 44.2 seconds, then paused, then began again, almost like a gimbal or gyroscopic pivot. Inside the hexagonal pattern were pulsed gaps, zones where no dust particles existed, and where magnetic field readings dropped to baseline. These zones weren't random, they formed spokes, 6 of them, arranged equidistantly, extending from the object's core out to the tips of the hexagon's edges. In engineering terms, this resembled a phased field geometry, a structure designed not to release energy, but to shape or filter it. NASA's Deep Space Network scientists flagged this immediately. Comets don't create symmetrical energy zones. They're reactive, volatile, and uneven. They don't phase their fields, they scatter them. But here, 3i Atlas was exhibiting the hallmarks of field sculpting. This discovery escalated concerns. If the object could sustain symmetrical geometry within an unshielded solar-facing structure, it meant one thing: stabilization through intentional design. The geometry wasn't accidental. It was being held, like a frequency cage or energy lens. This, in turn, suggested that the dust in the arc wasn't acting alone. It was likely suspended within a field, possibly electromagnetic or some kind of coherent plasma containment mechanism. And this raised the most critical question of all. Why? Why stabilize the arc in a symmetrical hexagon facing the sun? One theory came fast from the solar observatories in Hawaii: signal gain. If 3i Atlas was interacting with solar output, not merely absorbing it, but tuning to it, then the structured interface could be acting like a resonator, shaping incoming solar data, filtering wavelengths, or even embedding signals into solar feedback loops. That would turn the sun into a broadcast partner, or worse, a component in an unknown system. Because when celestial geometry aligns in real time with solar plasma behavior, the implication is clear: some intelligence, or deeply advanced automation, is in control. Interface lock geometry doesn't occur naturally, not across 6 equidistant zones, not rotating in harmony with core pulses, and not while wake scanning Earth. This wasn't random motion, this wasn't dust play, this was structured interface, and it was locked in. At 0932 UTC, the tail of 3i Atlas moved again, but this time it wasn't in response to solar wind. It was aiming. From ground-based telescopes in New Mexico to orbital platforms like SOHO and Hinode, instruments captured a coordinated twist in the main tail. Normally, tails simply trail behind a comet's core, blown by solar pressure and shaped by magnetic fluctuations. But the tail of 3i Atlas began rotating independently. It didn't just react to solar wind, it corrected against it. First, it shifted 4 degrees along the azimuth. Then it curled vertically, creating a subtle J shape. The curvature didn't match solar conditions, Earth's orbital path, or any known plasma current model. The trajectory appeared completely decoupled from external forces, which meant it was being directed from within. At first, scientists assumed it could be a product of electromagnetic asymmetry, a stronger ejection zone on one side of the nucleus causing the dust and gas to bend. But spectroscopic analysis showed the density of particles in the adjusted tail was equal on all sides. No imbalance, no asymmetric pressure, just deliberate orientation. This kind of behavior is known in spaceflight mechanics as vector tailing. It's how spacecraft use their own exhaust or ejection plumes to stabilize direction, essentially steering by shaping their own emission trails. The disturbing part? This was a comet doing it. A frozen object from interstellar space was exhibiting the kind of fine-tuned ejection behavior usually reserved for probes or satellites. But that wasn't the end of it. At 0937 UTC, a laser spectrograph on the Sofia Aircraft Observatory caught something even more startling. Pulsed emissions moving down the tail, spaced exactly 3.2 seconds apart. Each pulse glowed faintly in the far ultraviolet spectrum. They moved at a consistent speed and showed signs of low-frequency coherence, something completely unnecessary and physically impossible in random comet tails. This wasn't discharge, this was communication, either internally to align particles or externally as a signal. The direction of those pulses was crucial. They weren't moving away from the Sun, they were moving toward Earth. That single orientation detail changed the entire profile. The tail of 3I Atlas wasn't just an exhaust trail, it had become an antenna. And it wasn't broadcasting outward into deep space, it was pointing at us. What it was sending, or why, remains entirely unknown. But one thing was now undeniable. 3I Atlas wasn't reacting to our solar system, it was responding to us. By Doris 44 UTC, Earth's upper atmosphere, specifically the ionosphere, registered an anomaly. It wasn't an incoming object, it was a signal, subtle, repeating, and spread across multiple bands. The initial alert came from the HAARP, High Frequency Active Auroral Research Program, monitoring stations in Alaska. They detected a harmonic distortion in the upper ionosphere's reflectivity. This wasn't noise or background interference, it was structured. The frequencies weren't chaotic. They followed a deliberate oscillation, a slow rise, a plateau, and a sharp drop, repeating every 21 seconds. This pattern had never been observed before in global atmospheric behavior. More disturbingly, the anomaly wasn't regional. Similar patterns were recorded by China's ionospheric monitors in Xinjiang, Russia's polar auroral instruments, and Brazil's Embrace Space Weather Network. That level of synchrony is impossible under normal geophysical conditions. Normally, ionospheric shifts are driven by solar events, sunspots, coronal mass ejections, or magnetic storms. But at that time, the Sun was stable, no solar flares, no coronal disruptions, no geomagnetic storms. In short, the Sun wasn't doing it. Something else was. And all monitoring stations began tracing the pattern's source direction, not based on surface triangulation, but atmospheric phase delay. What they found was consistent. The signal appeared to be originating from the upper edge of Earth's magnetosphere, on a line that intersected the exact direction of 3I Atlas. The signal was extremely faint but coherent, matching the pulse tail beams tracked just minutes earlier. What started as a localized vector tail from the object had now become an Earth-responsive loop, a harmonic feedback between the object and our atmosphere. The mechanics of this are mind-bending. For any natural object to generate harmonic drift in Earth's ionosphere, it would need to 1. Emit at extremely low frequency, ELF, or very low frequency, VLF, ranges. 2. Maintain timing precision across hundreds of milliseconds. 3. Target Earth's atmosphere in a narrow enough cone to trigger multi-point resonance. No known comet can do this, and yet 3I Atlas did. One theory floated by MIT's radioplasma team suggested that we were witnessing intentional modulation, a kind of testing. If you wanted to know how Earth's magnetic shield reacts to external frequency input, you'd start by probing it, gently, at low power, with regular patterns. That's exactly what was happening. The waveform drift was soft, non-destructive, but it held a form that matched neither random oscillation nor background planetary noise. And the Earth responded. Our magnetosphere began exhibiting slight phase irregularities, pulses not matching the Schumann resonance, not triggered by solar variation. They were new, unlinked to Earth's normal feedback mechanisms. That sent one message loud and clear. 3I Atlas wasn't just emitting, it was listening. And when a comet listens to our atmosphere, the object in question can no longer be described as a visitor. It has become a participant in the electromagnetic architecture of Earth itself. At 0958 UTC, the final anomaly of the morning began. a cycle so consistent, so mechanical, that it immediately broke every model of comet behaviour. A deep space reflector array near the Canary Islands, part of ESA's lobe-scope radio reflection experiment, picked up something irregular while doing routine backscatter mapping. Every 42 seconds, a low-energy pulse hit the array. The signature was faint, just above background noise, but too regular to be natural. The frequency was in the microwave band, specifically 1.42 GHz, the hydrogen line. This is the frequency emitted by neutral hydrogen, and it's a key signature used in radio astronomy for mapping the structure of galaxies. But here's the catch. No known comet emits in that line, and this signal wasn't broad, it was narrowband, clean, timed, precise. The pulse was arriving from the direction of 3i Atlas. What made it stranger was the nature of the bounce. The signal didn't originate from Earth, it originated from somewhere else, past Earth's orbital range, struck 3i Atlas, and bounced back. That's what the reflector array captured, the reflected ping, and it came back every 42 seconds, like a heartbeat, like a measurement. Experts began calling it the echo cycle. One possibility was that Earth had been scanned. A more disturbing one, Earth was being ranged, just like radar systems that gauge distance based on echo delay. If 3i Atlas was reflecting an external signal at perfect timing intervals, then something else, farther away, possibly even behind it, was sending that signal. A separate emitter, and that suggested a multi-node system, a signal emitter, a reflector, and a receiver. This triad could only mean one thing: coordination. Some intelligence, or at minimum an engineered protocol, was measuring something in Earth's neighbourhood, using 3i Atlas as a tool. And that flipped the narrative completely. 3i Atlas wasn't just interacting, it wasn't just observing, it was part of something bigger, something calibrated, something orchestrated, and every 42 seconds we were reminded of it. At precisely 10:03 UTC, engineers at NASA's Jet Propulsion Laboratory noticed something they hadn't seen in over a decade: an unexpected blackout in the Mars data uplink. For nearly 3 minutes, the deep space transponder chain, responsible for relaying high-priority data from orbiters like MAVEN and surface assets like Perseverance, dropped into a dead zone. There was no signal degradation, no weak transmission. It was as if the stream had been snipped. The timing was odd. There were no solar storms, no Martian dust interference, and all relays were in optimal geometric position relative to Earth. But here's what made it more than a technical glitch. During that exact window, ESA's Mars Express orbiter, operating on a separate comms band, also lost telemetry. So did the Russian Trace Gas orbiter. All three systems from different agencies, running different protocols, across different frequencies, all went dark at the same time. That kind of alignment isn't a malfunction, it's a coincidence too perfect to ignore. The blackout occurred just as 3i Atlas was aligning with a point 1.3 degrees above the orbital plane of Mars, based on Earth's visual angle. It wasn't in direct line of sight to the red planet, but it was in the perfect relay path between Earth and Mars. And that's when a new hypothesis emerged. What if 3i Atlas wasn't just interacting with Earth? What if it was eavesdropping? A filtering object passing through key interplanetary data lanes, disrupting telemetry, not by brute force, but by routing signal energy away. Imagine a structure capable of magnetic, lensing, absorbing high-frequency data, distorting its transmission path, then allowing it to resume after a delay. It wouldn't look like an attack, it would look like silence, and that's exactly what happened. No spacecraft was damaged, no commands were altered. But Earth's ability to hear Mars, and Mars' ability to speak, vanished for 3 minutes, like someone had temporarily closed the gate. The implications here are staggering. If 3i Atlas has the ability to obstruct or redirect line-of-sight communication between two planets, it suggests it understands signal structure, transmission delay, and resonant disruption. That level of interaction isn't accidental, it's intentional design, and in that moment the object was no longer just passing through the solar system, it was modulating the information flow between two intelligent species on two planets, and that modulation, just like the harmonic signals traced earlier, fit into a broader, more unnerving pattern: control without contact. Just 5 minutes later, at 10:08 UTC, the Deep Space Network node in Canberra, Australia went offline. It wasn't the whole facility, it wasn't the antennas, it was one signal processor, a quantum coherent memory buffer used to handle long-range time delay correction for signal reflections. That may sound technical, but what it means is this. The component responsible for cleaning and aligning delayed signal echoes, especially from highly reflective deep space targets, suddenly froze. No surge, no spike, just a stall. The system, built to handle high-entropy noise from distant targets like Voyager and New Horizons, suddenly couldn't process echo delay timing. It was as if the laws of timing had changed. Engineers did what they always do, rebooted, rerouted, swapped to backup. But here's where the story shifts into the inexplicable. When they ran diagnostics, they found no hardware fault, no software bug, no magnetic interference. The buffer simply stopped responding during the exact interval that the 42-second echo pulses, previously tracked by the Canary Islands reflector, peaked in amplitude. The implication? The pulses from 3i Atlas weren't just hitting Earth's magnetosphere, they were now penetrating deep enough to disrupt Earth's time reference systems for deep space. This is beyond coincidence, this is signature interaction, and there's more. NASA's internal logs showed that during the blackout, the Canberra node received an undetectable packet, not a data file, but an entropy spike, a burst of randomness. It had no headers, no payload, no checksum, just entropy. Which, in quantum systems, could mean one thing. A test packet. Something, somewhere, had pinged Earth's deepest signal infrastructure to see how it responded to disordered input. And only one object was in the right vector alignment to cause that kind of interference. 3i Atlas. It didn't speak, it didn't send code, it simply broke the rhythm of Earth's time-aligned communication to deep space. And then, just as quickly, the signal buffer resumed, like a door closing, like a probe being withdrawn, like something had finished listening and moved on. At exactly 10:14 UTC, reports started arriving from United States Space Command, followed by mirrored confirmations from Allied stations in Diego Garcia, Guam, and the UK's Royal Air Force Station in Cyprus. Encrypted military comms in the ultra-high frequency band began to exhibit interference patterns, not static, not atmospheric noise, but a specific type of jamming, one that mimicked the pulse profile of the original Atlas signal first detected days earlier near L2. Normally, jamming has a telltale signature, broad-spectrum white noise, spike intrusion, or frequency hopping. But this was coordinated reflection. Military analysts reviewing the spectrograms described it not as an attack, but a mirror effect, as if something was bouncing back Earth's own encrypted frequency shapes, but slightly phased, delayed by microseconds and subtly bent in amplitude, like a copy of a copy. But here's where it becomes deeply strategic. The affected frequencies weren't public or satellite TV bands, they were hardened tactical channels, used only during simulated planetary defense operations and space asset maneuvers. In other words, off the grid until activated for defense readiness. How would an interstellar object, presumably non-intelligent, know which frequencies to reflect, unless it had already been listening for months, possibly years, and then waited for a moment when Earth activated its defense protocol, and answered back with distorted versions of our own encrypted signals? This wasn't signal disruption for chaos. It was a deliberate test of Earth's response mechanisms. To see what we do when our most protected systems falter, engineers tried to rechannel transmissions through backup bands. But the object, if it was truly behind this, adjusted in near real time, reflecting again, bending the signal just enough to make communication possible but untrustworthy. Imagine calling for backup, and hearing your own voice answer, just slightly off. Something was interfering, not to silence us, but to simulate our own systems, and in that mimicry lies the deepest threat of all. At 10:18 UTC, 4 minutes after the first jamming reports, an unrelated sensor triggered at Concordia Station, one of the most remote research facilities on Earth, buried deep in the Antarctic plateau. The station's sky mapping radar, meant for high-altitude aurora tracking and cosmic ray reflection, flagged something low on the horizon, too slow to be a meteor, too reflective to be debris, and positioned in a way that matched no known satellite orbit. It appeared, for 2 full seconds, on the limb of the southern sky, right where Earth's magnetic field dips most intensely toward the solar wind. The object, it was traced back to a reflection pattern that matched Atlas's projected echo field. This wasn't a direct sighting of 3i Atlas. This was something bouncing from it, an energetic shimmer, as if a pulse had arced through the upper ionosphere and curved across the planet's southern pole, and then everything went silent again. Except for one thing, the station's magnetometer, an instrument used to track subtle shifts in Earth's magnetic shield, showed a secondary harmonic forming just after the pulse. It wasn't a spike like a solar flare. It was a resonant ring, a wave signature that matched previous pulses but with a new twist. This time the energy didn't move outward from space into Earth. It moved laterally, across the southern field from west to east, tracing Earth's own magnetic latitude, which means the pulse wasn't just interacting with the planet, it was navigating it. Earth's magnetic field had become the medium, not the barrier, and South Pole sensors, isolated from most global noise, were the first to catch it. In less than 30 seconds, the wave passed beneath the field perimeter of Chile's radio observatory, was briefly picked up by Australia's VLF array, and disappeared beneath the southern horizon. We didn't see a spacecraft, we didn't detect heat. We traced the path of something intelligent using Earth's magnetic topology, like a subterranean sonar map. And the object guiding it had arrived, not above us, but within range. By the time Earth rotated further into the December 16th morning, every magnetometer, ionosonde and upper atmosphere radar from Stanford to Seoul was detecting anomalies. But these weren't the kind of disruptions that make headlines. No blackouts, no auroras, no EMP-like bursts. Instead, we found something stranger. Persistence. The ionosphere, Earth's high-altitude plasma layer, acts as a mirror for radio waves. It reflects, bends, distorts. But on this day it began to trap. Signals broadcasted from ground arrays were bouncing back not once, but multiple times, ricocheting between the ionosphere and the surface in looping patterns, building an energetic echo chamber around the globe. At first, researchers thought it was solar activity, but GOES satellites showed no spike. Then they blamed residual jet stream turbulence. But the troposphere was calm. Only one possibility remained, an artificial interaction, likely seeded from above. The shape of the echo patterns was unlike anything previously seen. Not circular, not elliptical. They were spiraled, tight vortices of energy that tracked with surprising symmetry. The geometry was unmistakable. Every spiral began near the coordinates of the last known trajectory of 3i Atlas, then spread outward like a synchronized ripple through the electromagnetic shell of the Earth. But here's what pushed it past scientific curiosity and into strategic alarm. Certain government agencies, especially those tied to defense-grade HARP, installations and over-the-horizon radar, noticed these ionospheric spirals were carrying data. Compressed, looped, repeating data that matched the reflected military signals from earlier chapters, but now wrapped in ionospheric spirals and bouncing between the layers of Earth's sky. Something, either Atlas itself or an associated object, was using Earth's own plasma boundary to replay our responses, to feed them back into our system in a controlled, modulated way. This wasn't atmospheric distortion anymore, it was a simulation test. Earth had become the chamber. Our frequencies, our patterns, our defensive posture were now being played back inside the very layer we use to communicate globally, and we didn't initiate it. We were being shown that someone, or something, was capable of listening, replicating, and embedding intelligence into the sky itself, as if the ionosphere had become a hard drive, and the writing process had just begun. At 12:01 UTC, without press briefings or public alerts, multiple national defense networks entered passive lockdown protocols, not because a missile was launched, not because a confirmed spacecraft entered low orbit, but because of the absence of something. Radar windows that should have reflected background noise, birds, planes, high-altitude balloons, were showing flat lines, not jammed, not overloaded, empty. All frequencies in the K-band radar spectrum dropped to near zero return. Earth's sky had gone acoustically still. To military analysts, this was worse than interference. This was a sign of passive shielding, an external presence absorbing or cancelling signal reflections without emitting its own. It was as if Earth had entered a cloaked observation field. In response, defense teams activated silent observation mode. No pings, no active radar sweeps, no responsive communication over high alert frequencies. This wasn't to avoid alerting an enemy, it was to avoid provoking a presence already inside Earth's sensitive detection web. Satellite uplinks were rerouted through oceanic relay points, ground stations dimmed power, and military-grade AI protocols took over autonomous observation, analysing patterns, feeding back into strategic command without human delay. Across Earth, a quiet consensus formed among observatories, labs, and defence centres. Something had crossed the final detection boundary. It wasn't approaching anymore. It wasn't simply echoing back signals or riding solar wind trajectories. It was here, possibly layered into Earth's magnetic boundary, possibly deploying silent probes, possibly observing our last moves before the moment we all feared. December 19th, a date that once marked a distant danger, now marked the deadline for understanding, and not everyone believes we'll get the answers in time. What happened on the morning of December 16th wasn't a strike, it wasn't an impact, it wasn't a flare or a flash or a burst that scorched the sky. What happened was contact of a different kind. Through spiralling echoes in the ionosphere, magnetic vortices that held steady under solar wind, and a silence across radar channels that felt more like an intentional pause than a technical failure, Earth became a participant in a dialogue it never meant to initiate. 3i Atlas is no longer a distant traveller. It's within the framework of our planet's outermost layers. And if we are being tested, probed, mirrored, echoed, and watched, the test may not be about technology at all. It may be about reaction, about what we send back when silence arrives, about how long we can listen before we feel the need to respond. And now, all eyes turn to one date. Not because it brings certainty, but because it no longer feels like the future. December 19th isn't days away anymore. It's the moment every defense system, every observatory, and every layer of Earth's shield is now counting down to. And whatever happens when that moment arrives will be recorded in the sky. The next signal is coming, and Earth has already been placed in listening mode. Until then, stay tuned, because what we just witnessed was only the beginning.